This is a lesson in university physics, calculus-based physics on RC circuits. In prior lessons, I had talked about how to deal with capacitors, just capacitors, in networks with a battery. I had also done that with just resistors and a battery in DC circuits. Okay, and so there's some equations, some things to recall about different capacitor and resistor properties and how they add in series and parallel for networks. What we're going to do is look at the time dependence of a capacitor in a circuit. Okay. From previous lessons, we know that the capacitor takes time to charge up. Okay. And because of that, we can look at a circuit at different periods of time in that charging up time, or conversely during a discharging time, right? It's a time dependent thing. We know that the amount of charge stored on a capacitor depends on that capacitor's ability to hold charge. Also, the resistors in there determine how fast that capacitor will charge up. Okay, there's a differential equation here. Notice that if I pick this loop here, I'll pick this loop and do a Kirchhoff loop on it. The voltage over the battery minus the voltage over the capacitor, notice, right? Q equals CV. And if I solve for voltage, then I get Q over C. This is the voltage over that capacitor. And then the voltage over the resistor is IR, right? V equals IR. And when I add those all together, they have to equal 0. That's just a voltage loop. Voltage loop. Good old Kirchhoff told us that. Okay. What I'm going to remind you is that the current is the differential with respect to time of the charge, right? dq dt. So when I put this equation together, I actually get, and this will look a little weird because I'm taking a negative sign, dq dt times r plus 1 over c q minus v bat equals 0. So if you've had enough math to work with differential equations, diffie q, this is just a first order differential equation. We have a nice proportionality going on here. There's only a few solutions that actually fit this differential equation, and an exponential is going to be what goes on. It's an exponential. It will charge exponentially and it will discharge exponentially, and because that comes from that differential equation. Okay, so I'm not going to get into the details, the math of solving that differential equation. I'm just kind of waving my hands and giving you the solution. Okay, what I'm concerned about is that you understand how the capacitor acts, how the capacitor is taking on charge or discharging at different points in time. Okay, so what we're going to do is we're going to charge the capacitor. What I'm going to do is I'm going to close this switch. You see the switch is open now, and I did this in PhET. You can look this up. You know, you can Google it on the internet. And Colorado has this nice applet for PhET that you can build DC circuits. This is a DC circuit. Notice this is a DC battery. And so this is a DC circuit. I have a DC battery in here. This is not an AC battery. This is a DC battery. And I have this switch open. Notice the switch is open. Because the switch is open, the battery can't do anything to the circuit. There's nothing going on in that circuit. What I'm going to do is look at the current as a function of time and the voltage as a function of time. And notice that with this summary table, I'm going to look at what the capacitor is doing at each section of time in that table there. Okay, so what I'm going to do is close the switch. When we close the switch, what we know is that battery is going to start pushing. When I close that switch, the battery is going to start pushing charge onto the capacitor, but the capacitor does not have any charge yet. So I'm going to close that switch and let the circuit play in the applet here. You can see conventional current. There's red arrows in every branch of the circuit going on, all right? That capacitor in here is easily accepting charge. The charge it has initially is 0. It's an empty capacitor. Because it's accepting charge really easy onto its plate, it's going to act like a wire. Notice that I have an acts like here. All right, so it easily accepts charge. And because it's easily accepting charge right at t equals 0, it's going to look like a wire. It acts like a wire. So if I redrew this circuit, instead of looking like this, if I redrew this circuit like I keep suggesting you do, at time equals 0, at t equals 0, this is what the circuit will look like. There's a battery. The capacitor will act like a wire. The resistor is still in that branch, and then the resistor is in the other branch. All right, that capacitor is acting like a wire in there. That's what that capacitor is acting like. If I were to find the current, for example, for this situation, I would do those two resistors in parallel with one another. It's as if that capacitor wasn't even there because it's easily accepting charge and is acting like a wire. Because it's easily accepting charge, there's no impedance really. The capacitor is not offering any impedance to that current flowing through that branch in there. So we're going to have an I max through that capacitor. Okay, and we can see that over when I look at the voltage and current graphs on this capacitor. The current through this branch, we're going to notice is at a maximum value. When I look at the voltage on that capacitor, remember Q equals CV. If I have not collected any charge yet, then the voltage across that capacitor will equal 0, and that's what we're seeing when I close that switch, is that there's 0 voltage across that capacitor. There's going to be voltage across the resistors because they have current through them, but not over that capacitor. Okay, so that is when time equals 0. If we let some time pass, that capacitor will start collecting charge. And because it's collecting charge, it's going to slow down the rate at which that charge is being accepted onto those capacitor plates. So let's look at that situation. I've switched over to the middle here, between t equals 0 and t equals infinity, that intermediate period in here. And it's transient. Notice, like I said, we had a maximum current happen, but now that that capacitor is starting to accept charge and there's some charge on that capacitor, it's going to offer some impedance, not going to accept charge as easily onto it. And you can see that that current is going to decrease over time as that capacitor fills up. All right, so C is filling up with charge. Okay, it's filling up with charge. It's going to reach a maximum charge. As it's filling up with charge, it's going to increase in charge. That current is going to decrease, and the voltage across that capacitor is going to increase. As it increases charge, it's going to increase voltage across that capacitor. And so that's what we're seeing over here, is we're going to have a decreasing current, increasing voltage over that capacitor. I'll talk about the equation. There's an equation that you can use, Q of t during that time, which is appropriate for between 0 and infinity. As we let that battery do its thing over time, that capacitor is going to fill up and reach a steady state, what we call a steady state. And that's when time is infinity, an infinitely long time after we close that switch. What we're going to notice the red arrows in this FET simulation here. There's no red arrows down the center, which is what we expect. Once that capacitor gets full of charge, it's not going to allow any current through that circuit. Or through that branch, I'm sorry. The circuit will still go because there's a resistor on the outside, but through that branch in the center there's going to be no current through there. And we can see that on the graph. There's no current in that branch with the capacitor. It's full. Notice that it's reached its maximum charge, it'll have its maximum voltage as well, and we can see that on the voltage chart here, maximum voltage. So what that capacitor is doing, because it's full, it's not allowing any current. When we redraw this circuit, what that capacitor is acting like is actually a break in the wire, right? There's no current getting through. It's not letting any current get through that resistor in that branch either. So if I redrew this circuit, the relevant where the current is flowing in this circuit is only through that outer branch with that R2 out there. There's nothing in the center. So a problem may ask you, what's the current through the battery after a long time? Notice initially at t equals 0, we had both resistors playing in, but because of how that capacitor acts in the circuit after a long time, it's only one resistor after a long time. So again, redraw your circuit. It depends at what period in time you're looking at and what that capacitor is doing at that point in time. So like I mentioned, we had a differential equation, and I said the solution is an exponential. We can mathematically model the charge on those capacitor plates with an exponential equation. This is a charging. When we're charging, notice that this gets smaller over time, right? So if we do 1 minus, it's going to get larger over time. We're going to start with 0 charge on the capacitor, and over time it's going to increase value. We have this time constant here. I'm going to talk about that in a second. The time constant tau, this is a Greek letter tau, is given by the resistance times the capacitance. Okay. So we're going to have some maximum charge over time. We can see that it reaches a maximum charge at some point, and it increases exponentially over time. And so that would be how you find a charge. I'm also going to note on this slide that if I wanted to find current, remember that current is the derivative of charge with respect to time. So you just take the derivative of that. And it makes sense when I take the derivative of this, I'm going to get an e to the negative t over tau. And the current goes to 0 over time, right? When we look at this, the current after a long time is going to be 0. So the current, even though the charge is increasing exponentially, the current is going to decrease over time exponentially. Okay. So that's charging a capacitor. What I'm going to do is look at discharging a capacitor. When we're discharging a capacitor, we have to look at different points of time as well. What we're going to do is we're going to take that switch and we're going to open it. So when I open that switch, it's essentially as if this part of the circuit isn't even attached anymore. The battery doesn't matter anymore. And when I redraw this circuit, I'm just going to have a capacitor with its 2 resistors in that circuit. Okay, so when you're looking at an equivalent resistance in this situation, those 2 resistors are in series with one another. So we do R1 plus R2 equals R equivalent. Okay. When we first open that switch, notice that the capacitor is completely full. The capacitor in the previous situation got to a maximum charge. Well, in this situation, when we detach the battery, we get rid of the battery, that capacitor still has that same amount of maximum charge on it. That'll be its initial charge. The capacitor in this situation is going to say, hey, I got a lot of charge. I'm just going to let it go, right? That charge doesn't want to be held together. It wants to dissipate through the circuit, and so it will start moving, and that capacitor will act like a battery. And at that point in time, because we have a maximum charge, we're going to have the maximum current through that capacitor, through that whole circuit, basically. And so when I look at that, when I look at current, notice we're at a negative value. That's right. When I take the derivative, you get a negative value in there. All right. So the current is a maximum value, and the voltage over the capacitor, notice it is a maximum value as well. It's going to have the maximum charge at that point in time, so it'll have a maximum voltage. It'll only lose it from there. As we let this capacitor discharge over time, So when we look at a period of time between 0 and infinity, after we open the switch and the capacitor isn't all the way discharged yet, it's going to have a decreasing charge. It's going to have a decreasing current because there's not as much charge to be pushing that current. And it's just going to be acting like a discharging capacitor in that time. Okay, we'll look at the equation, the Q of T, that happens during this time, Q of T, in a slide here, a few slides here. But when I'm looking at this, notice that those red arrows are still going. I have a decreasing current, right? That's why I said it has a decreasing current. That capacitor is not pushing charge as hard. And the voltage across the capacitor is also decreasing from its maximum value over time. It'll go to 0. Okay. After a long time, after a long time, this is DC. This will get to a steady state at some point. After a long time, that capacitor has discharged all of its charge. It's gone to 0 charge. Therefore, there's no current flowing through any part of that branch, that relevant circuit. And because there's no charge on it, the capacitor is going to act like some sort of inactive element. There's nothing going on in this circuit. And you can see that there's no red arrows designating the denoting the conventional current. 0 current, 0 voltage over the capacitor. Okay, it'll just discharge until nothing's left. So when we're modeling, when we have that mathematical model, and remember this is a differential equation, we don't have this part of the circuit over here. We only have R1 and R2 in series with one another. And when we're looking at this time constant, we're going to use the equivalent resistance in there. Use R equivalent with that. The charge, it'll be discharging. It starts with a maximum value, goes to 0 over time. Okay, if I wanted to find the value of the current at any time, I would just find dq dt. You all know calculus and how to take derivatives at this point. Just take the derivative and you'll be able to find the current at any point in time as well. Okay. Let's talk about this time constant real quick. I referenced it a couple of times previously. The time constant is R times C. R, keep in mind, is the equivalent resistance of the circuit of interest. I had always redrawn these circuits, right? In this situation, R equivalent is going to be 2 resistors in series with one another. I know they look like they're in parallel, but when I get rid of this side of the, rid of this side of the circuit, the current will flow through this one and then up through this one. They're not in parallel, they're in series for the discharging circuit. So when you're looking at that equivalent resistance, make sure you have identified the correct circuit of interest. Same with a capacitor. You might have more than one capacitor in a circuit. What the time constant says is, because we're working with exponentials and natural logs and that sort of thing, the time constant is the amount of time it takes for a circuit to discharge to 0.632 of its maximum value or discharge to 0.368 of its maximum value. That's what a time constant is. So we're looking at this point here or this point here. Okay. It has either charged to a certain value or discharged to a certain value after a time constant. I think of a time constant as a descriptive way of saying how quickly will it discharge or how quickly will it charge. If we look at the time constant, to me it's equivalent to like a half-life of an element. It tells me how long it will take for it to decay 1/2. In this situation, it's how long will it take to charge to 63% or discharge to 37%. Okay. What I have for you here is a nice summary slide that you can take a screenshot or copy into your notes for when you're solving problems. Okay, it has summary about whether it's charging and what that equation is, discharging, what that equation is, and what the capacitor acts like at different times. Remember to redraw your circuits. If you need a current, just take a derivative of the charge, and you're good to go. So I'll have another video to solve problems. Look for that video for how to solve charging and discharging circuits.